Okay, hello, welcome to our next video. We're going to do a video now on radians, so that's going to be your title. I'm actually going to kick off by just showing you kind of the point of radians, and then we'll go back to thinking about what they actually are. So we do need to just define them first of all. A radian is a way of measuring an angle, effectively. Throughout all of your schooling you've been using degrees. Now we're just going to throw another one into the mixture, radians. And then I'm going to show you first of all kind of why we do that. So first of all, 360 degrees, now this is our definition, 360 degrees is what you're used to having for angles about a point, a whole circle if you like. You can think of it as being 360 degrees. But effectively 360 degrees is 2 pi radians. And we sometimes see that as done with a little c. So that's quite nice. 360 degrees is 2 pi. Obviously, if you were to halve one, so 360 degrees would become 180 degrees. We know that as being like half a turn. You'd halve the other one, so 180 degrees is pi radians. Let's just write that down as well. 180 degrees is pi radians. And you can see it kind of building up from there. So what I want to do now is I just want to talk about our application of this a little bit in terms of a couple of formulae. So let's just look at some circles. So I wonder if I can do this. There's a beautiful circle. What I can do is I can say the centre is going to be about there. That's the centre. And if I draw something here, and I needed to find the arc length, say this distance around here that I've drawn with an arrow. Now, when you had degrees, what we would do, you'd have a radius of r, you would do, well, you'd find out the circumference of the whole circle, and then what you would do is you would find the section that you wanted. So say we called this angle here theta. What you would do previously is you would do, so let's just deal in degrees like we're used to doing. It would be the arc would be equal to 2 pi r times theta out of 360. That's what you would want as a fraction of the whole, the theta out of 360, and then you can work out what the arc length is. Now, if we do the same thing in in radians, I keep drawing those lines on there. Let's try and stop that. I'll rub it out a little bit. Okay. Now, if I do exactly the same thing in radians, my arc is here. Again, it's still 2 pi r times that angle, theta, but now it's out of 2 pi. Hopefully you can see where I'm going with this. It's actually made things a lot simpler. I've just created a fraction with a 2 on the top, a 2 on the bottom, a pi on the top and a pi on the bottom. So now it is r theta. So my arc length becomes a much easier calculation if the theta is in radians than if previously here if the theta was in degrees. That's one of the purposes of it. The second one is if you're looking at the area of a sector. So let's just look at how that one builds up. This is something you're going to need to know. Make sure this is in your notes and kind of box around it, whatever you do. Your arc length, when you're dealing with radians, is the radius times by theta. Okay, so now let's look at the area of a sector. So I can write area of sector. And what have we got? There's the centre. If you're finding the area of a sector, what you would do with degrees, again, first of all, let's just recap that from GCSE. You would do pi r squared and then you would multiply that by the fraction of the circle that you've got, which would be theta, obviously our radiuses are, pi r squared times theta over 360. So that's in degrees. Radians though, you're going to do the same idea. Let's go in red. Pi r squared times theta out of the whole circle. Now remember, the whole circle now is 2 pi. And so we can again simplify this a bit. I've created a fraction where I've got pi's that cancel, and all I have is that r squared theta over 2, or as we tend to write it, a half r squared theta. Again, it's a much easier formula to be able to use and apply. So we can say this was the area of sector equals this. Again, box it. This is an important thing that you're going to need to use and apply. Area of sector is half r squared theta. And that's in the case that you're dealing with radians, your theta is a radian type question. So what I want to do now, just to finish off the video, it's a nice quick one to start with. Just do a couple of questions that you might see, a couple of examples, and then you can get on with some work hopefully during next lesson. So let's go down to one side. Let's just go for a little example question. Okay, here's a question that I've just put in. Find the length of the arc of a circle of radius 5.2 centimeters. The arc subtends, that was one word, but my iPad's made it two. The arc subtends an angle of 0.8 radians at the centre of the circle. The first thing I'd like to do is just give this a little bit of context. Oh, I don't need that to be blue, but I do want to write in a different colour. Okay, this 0.8 radians. Just have a little think to yourself how large that is. Now, how large is that? Well, we said by definition that 2 pi is 360 degrees. Now 2 pi we know has a value of 6 point something, we don't need to think too much beyond that. Pi we said was 180 degrees, so that's 3.14 and so on. So actually, if I'm giving a little bit of context, I'm going to say that 0.8 radians is less than a quarter of a circle. So actually what we've got, if I draw a circle, we're going to draw a decent diagram of what's going on here. And we'll use that circle there, not too bad. It's less than a quarter of the circle, so what we've got is we've got this here. Well, that actually looks close to being a quarter, but never mind. 0.8 radians and a radius of 5.2. So my arc is as simple as doing radius times the angle which is 5.2 times 0.8, which equals 4.16 centimeters. And there's our answer. Nice and easy. Radians are good. You're going to argue with me, I'm sure, over the next few weeks, but radians make this so much easier. Okay, next one. Okay, this is a great example question. I love this. Okay, here we go. A plot of land is in the shape of a sector of a circle of radius 55 metres. Of course it is. All land comes in sectors. Anyway, the length of the fencing that is needed to enclose the land is 176 metres. Calculate the area of the plot of land. Okay, let's just work out the angle first, or let's just have a little diagram of what's going on in order to start labelling things. So I've got a sector, which I'm going to label like this. Nice pizza slice. So my sector is a radius, first one I'm looking at, 55 metres, so that's fine, I can label that. This can be 55 metres. Obviously the radius is going to be consistent, 55 metres. So I've used up 110 so far, it's 176 in total, because the perimeter of the fence is 176. So I know that arc length is going to be 66 meters. Okay, first thing I need to do is I need to work out this angle. I need to know what this angle is here. And obviously we're dealing with radians, we're going to do that in radians. So, we know our formula for our arc length, we've just applied it. So our arc length L, let's go for a different colour. Arc length L is equal to the radius times theta. Well, what do I know from that? I know my arc length, 66, is equal to 55 lots of theta. So actually, my theta is equal to 66 over 55, which I believe simplifies down to theta having a value of equaling 1.2. Remember, we're dealing with radians. 1.2. Perfect. Right, it's coming together. Now I need to use my second formula to work out the area. So the area of this pizza slice, if you like, this whole thing, what's that? Well, my formula that I've just learnt in my maths video is going to be, what colour should we go? Red. So my area equals a half r squared theta. Nice and easy. So that equals a half times 55 squared times 1.2. Again, easy peasy. What's a half of 55 times 1.2? I think using grabbing for my calculator. I don't know my 55 times table. Certainly not to multiply it by 1.2. I get an answer of 1,815 meters squared. So that is my area. And that's the second question done. And that was a nice question because we had to use both formulae. We had to use the L equals r theta, as in arc length equals r theta. And we also had to use our area equals a half. Oh wow, look at this. Oh, I've got an arrow. Area equals a half r squared theta. So that's our two formulae that we've used. Hopefully we've used it in a way that you can see that there's the benefit of having radians instead of just being told that they're there. And when we come together next time, we'll discuss or we'll work through trying to apply this in different areas. But that's it. That's our video done for today. Well done. Thanks for tuning in.